All right, so doing a percent yield problem step by step.
Are you taking a video?
Huh?
Are you taking a video?
Am I taping a video?
Yeah.
I'm recording this.
Just because you kept saying it, so I was like, what?
All right.
Here we are.
All right, so the question is, what is the percent yield when aqueous solutions containing 3.27 grams of hydrochloric acid and 7.26 grams of calcium hydroxide are mixed, and 2.5 grams of calcium chloride is collected by evaporation of the water? Okay, so interpreting the problem is like the first thing you got to do. You got to interpret the problem first. We've got two reactants. We've got 3.27 grams of hydrochloric acid. Hydrochloric acid is one reactant. We've got 7.62 grams of calcium hydroxide. That's another reactant. The way this is stated, it's saying we have two solutions, two chemicals in two different solutions. We're mixing them together, and we're getting this product. So we're reacting calcium hydroxide and hydrochloric acid, and we're getting this product, 2.5 grams of calcium chloride. Okay? So what we have to do is to write a balanced equation to describe this reaction. We're going to need the balanced equation to do this math anyway. And we know that because we're trying to find an amount of a product. Okay, it says we're collecting this amount. What's the percent yield? Tells us we're having a product. So we've got to be able to write the equation and balance the equation in order to get the molar ratio for stoichiometry that we're going to need. Okay, so the first thing I'm going to do is write a balanced equation based on what I have in the problem. So you need to know what hydrochloric acid is. Well, yes, it is HCl. The hydro prefix means we have a binary acid. So chloric means there's chlorine in there, and you put hydrogen on the front to make it an acid. Okay, so we're going to write HCl here. Now it says it's an aqueous solution, so we're going to identify that as being AQ. And then calcium hydroxide, well, calcium is Ca. Hydroxide is the polyatomic ion, OH. Calcium has a 2+ charge, and you know that because it's in the second column of the periodic table. And all of those elements in the second column of the periodic table are going to have a 2+ charge when they're in an ionic compound. Let's see, I'm trying to find the right periodic table that we use in this class on tests. Of course, I don't have the right set of references here. I'll just go to this one. It's a different periodic table than used in this class, but that's okay for this. So calcium is in the second column. All of these elements have a 2+ charge in a compound. And hydroxide is one of the polyatomic ions that, in this class at least, you're supposed to memorize, and that has a 1- charge. So if this has a 1- charge, it's a 2+ charge, I'm going to need two of these to balance out that 2+ charge. And hydroxides are mostly insoluble, but there are some exceptions to it. And if you go to the solubility rules, and in this class you're supposed to memorize the solubility rules. If you haven't memorized them, you probably need to work on that. Hydroxides are mostly insoluble except for group 1, strontium and barium, so calcium is not an exception. We're going to list that as solid. Okay, it's insoluble, and even in water it's going to be listed as a solid. And so now we've got to know what our products are. So I have an acid and I have an ionic compound. I know this is an ionic compound because it contains a polyatomic ion. There are also ionic compounds that are made of metals and nonmetals. But either one of those is going to tell you, one of those two will tell you if you have an ionic compound. A metal bonded with a nonmetal will create an ionic compound most of the time, and the presence of a polyatomic ion will tell you have an ionic compound most of the time. So we have an acid and an ionic compound, and when we have a reaction like that, we're going to have a double replacement reaction. Okay? So the front part of this has got to join up with the back part of that. The outsides join up with the outside joins up with the outside, insides join up with insides. So H goes with OH, and that's water. Okay? Normally we write water H2O, but HOH is still water. There's no heat here, no significant amount of heat, so this is going to be a liquid. Water without a lot of heat is going to be a liquid. Calcium is going to join up with chlorine. Calcium is 2+. Chloride is 1-, so we're going to need 2 chlorines or 2 chlorides. Now, the reason you know that chlorine has a 1- charge is that it's in column 7A. And in a binary compound like this, and binary means only two elements, in a binary compound, chlorides have a 1 negative charge. Alright, so we know if this is aqueous or not. It kind of tells you that. It says it's collected by evaporation of water, so it has to be dissolved in water, that the water evaporated to give you this compound. So that alone would tell you it's aqueous. But you can also look at the solubility rules and see that chlorides are almost always aqueous, or they're almost always soluble, and therefore if there's water around, as there is, then it's going to be aqueous. So chlorides are right here. They're almost always aqueous, except when they're bonded with silver, lead, or mercury, and that's not silver, lead, or mercury, so this is going to be aqueous. Alright, so that's the unbalanced equation. Now we've got to balance the equation. So we're going to list all of our elements vertically like this: H, Cl, Ca, and O. And we're going to make a kind of a grid, a little mini spreadsheet here to make an atom inventory. And we're going to count all of the hydrogens on the left side. I've got 1 here, and there's 2 outside the parentheses, means I've got 2 of everything inside, which includes 2 hydrogens. So that's 1 plus 2, or 3 hydrogens. I've got 1 chlorine, 1 calcium, and 2 oxygens. On the other side, I've got 2 hydrogens to start. I've got 2 chlorines to start. I've got 1 calcium, and I've got 1 oxygen. And so what we want to do is to get the number of atoms on both sides to be exactly the same. The only thing we can do to make that happen is to use coefficients. We cannot change these subscripts. We cannot change the formula. We can only put coefficients in front of the formulas to change the number of each of these formula units or molecules, whatever they happen to be. Alright, we're going to save hydrogen for next to last and oxygen very last. And we're going to start then with chlorine. Since I have 2 chlorines on this side, to get 2 on this side, I need a coefficient of 2 in front of the species containing the chlorine. And that's going to change the number of hydrogens and chlorines. Now we've got 2 hydrogens here, and I've got 2 hydrogens here, so I've got 4 hydrogens. And then I've also got the 2 chlorines, which is what we were seeking a while ago. Alright, we're going to save oxygen for last. We're going to do hydrogen next. Since I have 4 hydrogens on the left, to get 4 hydrogens on the right, I need a coefficient of 2 in front of the species containing hydrogen. And in the hydrogen, or in this formula, there are 2 hydrogens. So 2 times 2 is 4 hydrogens. It also changes the number of oxygens over here to 2. And now the number of atoms of each of these elements is exactly the same. So this is our atom inventory. We now have a balanced equation. Alright, now we need to find, so our first step, if you want to talk about, I like to call them stages, because when we say steps, there's a lot of steps in here. But the first stage of this process is to find a balanced equation. That's what we did. Okay, so this was finding the balanced equation, first stage. Second stage is to determine what the limiting reactant is. Now there's about 3 ways that I can think of to determine what the limiting reactant is. The way that I teach you to do that is to do a mass-to-mass calculation from one reactant to the other, and then judge from the amount of the second reactant that you get, what is the limiting reactant. I'm going to show you that now. Now you can do it, like I say, one of several ways. That's the way that I teach it. Okay, it just seems to be simpler for most of my students. So I'm going to choose to start with one of these 2 reactants. Hydrochloric acid is listed first. That's what I'll start with. Okay, I'm going to start with 3.27 grams of hydrochloric acid, and I'm going to put that over 1. You could start with calcium hydroxide. Doesn't matter. You should get the same result. I'm going to put that over 1. Always start with your starting amounts over 1, at least for the kind of stoichiometry we do in this class. Now there are other kinds of problems that involve stoichiometry beyond Chemistry 1 where you might start with something else. But in here, I always teach students to start with their starting amount over 1. And the first step then is to convert this into moles. And to convert grams or mass into moles, I need to calculate the molar mass. And so we're going to take the atomic mass of all the elements in the formula, all the atoms really in the formula, and get the sum of those, and that sum in units of grams will be the molar mass. So in this case we have 1 hydrogen, and the atomic mass of hydrogen is 1.008, and I've got just 1 of them, and since I've got 1 of both of these, I'm not going to multiply by 1. I'll do some multiplication when we get to the calcium hydroxide here in a minute and show you how that works. But if I just got 1 here, 1 of these, 1 of each of these, there's not much reason to multiply by 1. Would you say that's true? Okay. And so I'm going to do chlorine here, and chlorine is 35.45, I believe, on your periodic table. And so I'm going to add those together. Now, I should have lined up my digits better if I wasn't going to do any multiplication, because if I line up the digits, or line up the decimal place, I should have an 8 over here on the side. That 8 is going to result in an empty slot over here. So we're going to round off a number when we get to the end. Now, you need a scientific calculator for this test, okay? Make sure if you don't have one, you get one, because we're getting to that point in the semester where using one of my calculators is going to kind of be counterproductive. You need to get a calculator, learn to use your calculator, and get to the point where you're comfortable with it, and learn its syntax, okay? So I'm going to take 1.008 and add 35.45, and you might be able to do this in your head, and that's fine. Okay, and so this 8 then results from an empty slot right here next to this 5. And that means that 8 is insignificant. I'm going to underline it. This is grams of hydrochloric acid, but we're going to round off that 8. Okay, now the way you're taught in grade school and high school to round off is if this number is 5 or greater, you're going to round up the number next to it, or the digit next to it. So it's 36.46 grams of HCl, and that's the molar mass. But to hammer home this idea that this is molar mass, I require my students to always write down that this is equal to 1 mole of HCl. It also helps to reinforce the fact that the conversion unit we're going to build is based on the fact that we have something on the top equal to something on the bottom. So down here we've got 36.46 grams of HCl. I'll put that on the bottom. Okay? Because I want to be able to cancel these units and this species. So canceling grams because I've got the one on the top, one on the bottom, and species because I've got one on the top, one on the bottom. I can do that. The other side of this equality statement goes on the top.
Why wouldn't it be 2 moles if you have 2 of HCl?
So what I have here now is a fraction that actually equals 1. If we just looked at this fraction equals 1. What we're doing then by multiplying this number by this fraction is changing the units of measurement without changing the amount. And so we can cancel the grams just like x's and y's in algebra. You can cancel x's and y's if they're on the top and bottom. Okay, cancel the HCl in the same way. And we now have moles of HCl. Now we're going to move forward because next thing we've got to do is convert from the moles of HCl to the moles of the other thing we're looking for. And in this calculation where we're trying to find what the limiting reactant is, we're going to be going to the other reactant. This is one reactant, this is the other reactant. Okay, sometimes they're called reagents. If we're using them in a lab and I had an amount of this, that'd be called a reagent. All right. So I'm going to look at the coefficients in front of these two species, and those can be individual formula units or those can represent moles. In this case we want to represent moles because we want to cancel moles. So here I've got 2 moles of HCl. That's going to go on the bottom because I want to be able to cancel that. And the 1 mole of this is going to go on the top. Alright, so moles are going to cancel and HCl is going to cancel. Alright, now I've got to convert moles back into grams in order to compare that number against the number in the problem up here, 7.62 grams of calcium hydroxide. So I've got to calculate the molar mass of calcium hydroxide. And so the atomic mass on this periodic table in this class for calcium is 40.08. The atomic mass for oxygen is 16.00, and for hydrogen is 1.008. But now we've got more than one of the oxygen and hydrogen. So I'm going to multiply all these. This is times 1 because there is one of those. This one's times 2 because there's 2 oxygens. The parentheses means I'm multiplying everything inside that. And there's 2 hydrogens, okay? And so I've got 40.08 calcium. I've got 32.00 for the oxygen. And I've got 2.016 for the hydrogen. And we're going to add those together. Now we've got a situation where there's an empty slot here above this 6. Now I know in math classes you've been taught to put zeros there. We can't do that in this class because those zeros really represent something. They represent the precision of a measurement. And if you add zeros there, you're lying about the precision. So we can't put zeros there. But if you like to have a place keeper, you can put an arrow there. It's not required that you put an arrow there, but you can put an arrow there. So 6, 9, 0, 4, 7, 74.096. Okay? So this 6 is insignificant because we don't know what those two digits would have been if we'd had them. I'm going to underline the 6. This is grams of calcium hydroxide. But we're going to round it off now to get rid of that 6. So that 6 rounding off, since it's 5 or greater, makes this adding a 1 to this, making it 10, which means the 1 goes here and a 0 goes there. So 74.10 grams of calcium hydroxide. And again, we're going to say that's equal to 1 mole, in this case, moles of calcium hydroxide. All right? So now we have another equality statement. It's an equality statement because it's got an equal sign, it's got measurements or calculated numbers on both sides along with the units and species that go along with that. And so now I'm going to put up here, I want to have moles on the bottom. So this side of the equality statement on the right here goes on the bottom here to match the units and species on the top here. 1 mole of calcium hydroxide. And then on the top is 74.10 grams of calcium hydroxide. And when we cancel the moles and the species here and here, we're left with grams of calcium hydroxide, and that's what we want. We want to find grams of calcium hydroxide. So now we have to do the math. Now the way that I teach my students to do the math is to take and multiply everything across the top. Okay, then hit equals in the calculator, then divide by one of the things on the bottom that you need to divide by, hit equals again, and then divide by the second. So let me show you how that looks on my little inexpensive calculator here. Okay, so I mean you can use a more expensive calculator. I'm just going to show you on this one. So turn it on first, I guess. And I'm going to start with 3.27. I'm going to multiply. I don't need to multiply by 1 because that just gives me the same thing. I'm going to multiply by 74.10. Okay, I'm going to hit equals. Then I'm going to divide by 36.46. Hit equals. Then I'm going to divide by 2. Okay, and then I get this answer. All right. All right. Now we need to find the correct number of significant digits for this answer. I want to look at all the measured and calculated numbers in the problem. These are counting numbers. These whole numbers are almost always counting numbers, but these fractional numbers will be measured or calculated numbers most of the time. And all the measured and calculated numbers, this being a measured number, this being a calculated number, this being a calculated number, you know those two are calculated numbers because we calculated them. But all this measured and the two calculated numbers, the one with the least digits is this first one. And we want to have our final answer have the same number of digits as the part of the problem that has the least digits. Okay, so we want 3 digits in this answer. 1, 2, 3. Underline everything else to show those are insignificant. This is grams of calcium hydroxide. And we're going to round that off to 3.32 grams of calcium hydroxide. All right. Now this number will never be used again. Okay, we're only using this number to figure out what the limiting reactant is. And when we compare this number against the one in the problem up here, 7.62 grams of calcium hydroxide, we see there's a significant difference. This number right here is the amount of, or the mass of calcium hydroxide that will fully react with this mass of hydrochloric acid. Since we have less here than we have in the problem has a lot more, that means this is how much is going to be used up, and there's going to be a lot more left over. Therefore, this species, calcium hydroxide, is in excess. We've got more than we need of the calcium hydroxide. So this is our excess reactant here, okay? Which means hydrochloric acid over here is the limiting reactant, okay? All right. Since hydrochloric acid is the limiting reactant, then to calculate the theoretical yield, we have to start with the given amount of hydrochloric acid. You always start with the given amount of limiting reactant. Okay, the given amount, the amount in the problem, not the amount that you use down here or that you calculated down here, the given amount of the hydrochloric acid or whatever your limiting reactant happens to be. So we're going to start with we'll start the same way we did here. It just happens to work out that way this time. Sometimes it wouldn't. Okay, but it just happened to start out the same way here. We're going to start with the given amount, 3.27 grams of HCl, put it over 1. We still got to convert it to moles, so we still need this same molar ratio. We just happen to be lucky here to have it look exactly the same. 1 mole of HCl, 36.46 grams of HCl. And now we get to the molar ratio. Now the molar ratio step is going to be different because we're no longer trying to find this reactant here, this calcium hydroxide reactant. Now we want to find the product. And the problem says we're looking for calcium hydroxide. Okay, so we want some calcium chloride rather. We're looking for this stuff right here. Okay, so looking for calcium chloride. That's our product. All right, so we're going to put the 2 moles of HCl on the bottom. But this time we're going to put the 1 mole of calcium chloride on the top because that's what we're looking for here. Okay, let me go back and make sure I cancel units and species. Now we got to convert this into grams, so we need another molar mass calculation, this time for calcium chloride. So calcium is 40.08, and chlorine is 35.45. And we have 1 calcium, and we have 2 chlorines. Okay, add these together. That's 110.98, and there's no empty slots over here this time. Okay, so there's no worries about rounding off. There's nothing to round off. Okay, so in this case, then we just got grams of calcium chloride. If there's no empty slots when you're doing addition and subtraction, empty slots to the right. If there's no empty slots to the right, you don't have to round off. And so that is equal to 1 mole of calcium chloride. Started to draw an arrow. So used to doing arrows, don't need an arrow though. So let's get rid of that. We don't really need that line right there. Okay. Alright. So now we have an equality statement suitable for doing this last conversion down here, or at least the last conversion in this stoichiometry problem. We've got moles on the top here, so we want these moles on the bottom here. 1 mole of calcium chloride. And we want the mass on the top, 110.98 grams of calcium chloride. Cancel out moles and cancel out calcium chloride, and we're ready to do this math. Okay. So 3.27 times 110.98, it equals, then divide by 36.46, hit equals, then divide by 2. Okay, and I got 4.97 674 9863. Okay, we have grams left and calcium chloride left. And again, we're looking at the measured and calculated numbers in the problem to figure out the significant digits. This is the one, this number here is the one with the least digits. So we want to match the number of digits here. 1, 2, 3, those are our significant digits. Underline from here over. And draw an arrow to show we're rounding off. That's the only operator I allow for you to show you rounding off. And so this 6 then is going to make this 7 round up to an 8. 4.98 grams of calcium chloride. And that is the theoretical yield. Okay? Alright, we got one more step to go. So we've gotten through 3 steps now. Okay? We balance the equation, or stages. Stage 1, balance the equation. Stage 2, determine what the exit or limiting reactant is. We found out this was the excess reactant making the other reactant the limiting reactant. So we found out by doing this what the limiting reactant was. So stage 2 is finding the limiting reactant. Stage 3 is finding the theoretical yield. Stage 3 is finding the theoretical yield. And the last stage is to calculate percent yield. And for percent yield, it's always actual yield over theoretical yield times 100. Always actual yield over theoretical yield times 100. The actual yield in this problem is this 2.59 grams of calcium chloride. It says that's what we got when we collected it by evaporation. Okay, so we're going to put that 2.59 grams of calcium chloride over the theoretical yield, and this is the theoretical yield here, 4.98 grams of calcium chloride. And then we're going to do that math, and we're going to multiply by 100 to get a percent yield. Okay, notice units are going to cancel. Anytime you have a percent, now I've seen it other percents that were set up without this, but for chemistry it doesn't make sense really any other way. But for chemistry, for sure, if you have a percent, you have to be able to cancel units. If you can't cancel units, you've set up something wrong. Okay, it just so happens that for percent yields, and that's one of the very few times it ever happens, but for percent yields, the species will also cancel. Okay? All right, let's do this math. 2.59 divided by 4.98. Hit equals, and then times 100. And we get 52.008. Actual yield over theoretical yield. Okay, and this is a percent. We need to round off properly. Since this is a division problem, we're going to use the one of these, whichever one of these numbers has a smaller number of digits. Both of them have the same number of digits, 3. Just for clarification, this 100 is never used for significant digits because that's an absolute number. It's defined as being 100. So we have 3 digits here and 3 digits here. We want 3 digits in our answer. Underline everything after the first 3 digits. Draw an arrow to show that we're rounding off. And we have 52.0% yield in calcium chloride. All right. So I was asked to do a problem then where we are working with gas volumes, and I just had this problem already written out, so I just kind of tweaked it a little bit. And this one we're going to produce hydrogen, and I just decided to do it with hydrogen gas at STP to satisfy the question. If ammonia gas is decomposed into hydrogen and nitrogen gas, and if 12 grams of ammonia produced 20.80 liters of hydrogen gas at STP, what was the percent yield? So this is a decomposition problem. We've got ammonia gas, that's NH3. Ammonia is NH3. Ammonium is NH4 with a plus sign. And we're going to decompose it. So there's no other reactant here. There will not be a limiting reactant here. Okay? Well, there could be a limiting reactant on the test. In this case, there isn't, because decomposition, there's no, it doesn't make sense to have a limiting reactant. There's only one reactant. Okay? And so we're going to decompose it into nitrogen gas, and you need to know nitrogen gas is N2. Okay? And we're producing also hydrogen gas, it says, and hydrogen gas is H2. Okay? But we have to balance the equation. And so we're going to list all of our elements, N and H. Huge list of elements, huh? Okay? Have y'all balanced the equation already? So we can start with 2 of these, which will give us 2 and 6, and I'll put a 3 here, and that'll give us 6, and that's balanced. Okay. All right. So we're going to start then for our stoichiometry. We don't have to calculate to find a limiting reactant. We can go straight to the product here. Okay. Because there's only one reactant. There's only one reactant. There's no limiting reactant. To have a limiting reactant, you've got to have more than one reactant. Okay? So we're going to start with this. This is the limiting reactant because there's no other reactant. That makes sense? So you don't have to calculate it if you already know what it is. Sometimes the problem will tell you, let's say you're burning ethane in air. Well, what's the limiting reactant? Ethane, because there's plenty of oxygen in the air, right? So, and sometimes you don't need to calculate a limiting reactant, but if you don't know which one is the limiting reactant, then it's incumbent upon you to figure it out first. Okay? All right. So let's see, we've got 12.0 grams of ammonia. I'm going to put that over 1. We need to convert that into moles, so we're going to have to do a molar mass calculation to find out how many moles there are in this substance. How much mass there is actually in 1 mole of this substance. So we've got nitrogen and hydrogen. Nitrogen's atomic mass is 14.01. 14.01. Hydrogen's 1.008. We've got 1 nitrogen and 3 hydrogens. 14.01. 3.024. Okay. So 17.034. That's grams of ammonia. But we've got this empty slot over the 4. And so we don't know what this number would have been if we knew what that number, because we don't know what the number was going to be. So we're going to underline that and round it off. And we've got 17.03 grams of ammonia equals 1 mole of ammonia. Okay, and so now we have an equality statement to build a conversion unit here. We want to match the units and species that are in the top of this problem with what we put on the bottom here, and it's on this side of the equality statement. And the 1 mole goes in the top. Okay, and so we can cancel grams and ammonia. And now we need a molar ratio. And the molar ratio between what we're starting with, ammonia, and the stuff we're looking for, hydrogen, is 2 to 3. So there's 2 moles of ammonia and 3 moles of hydrogen. Okay. All right. And so now we need to convert the moles of hydrogen into the volume. Okay. To compare this volume, we've got to have a volume down here. So we don't need a molar mass here. Molar mass is unnecessary. All we got to know is by memory that 22.4 liters of a gas, and hydrogen is a gas, so we can write H2 here, equals 1 mole of hydrogen gas at STP, right? And it is at STP. So moles of NH3 cancel. And then we've got moles of H2. Now we're going to convert to liters using this equality statement. 1 mole is going to go on the bottom. 22.4 liters is going to go on the top. Oh, not times. Equals. And we're ready to do this math. Well, I got to cancel units here and species here. Oh, I put in 22.4 instead of 22.4, so let's do that again. Alright, so across the top, hit equals, divide separately the things on the bottom, so divided by 17.03 equals, and then divide by 2. And I got 23.67. Did you guys do the math and get the same thing? 23.67. Okay, and that's liters of H2. And we need to round off again. Looking at the problem, this number and this number have the least digits. They both have 3, so we want 3 digits in our final answer. Underline everything after the first 3 digits. round off, we get 23.7 liters of H2, and that's our theoretical yield. Okay?
How did you get 22.4?
Okay. So now that we got a theoretical yield, we can figure out a percent yield. If this is our actual yield, and that's what it means, we produce this amount, all right, then we're going to take that actual yield of 20.80 liters of hydrogen gas and put it over 23.7 liters of hydrogen gas. Actual yield is this, over theoretical yield, that's this. Then actual yield over theoretical yield times 100 will give us a percent yield. And 87.76. And we want to round off to the correct number of significant digits. This number here, this measured or calculated number has 4. This one has 3. We want 3 in our final answer. So 87.8% yield in H2.